Welcome to Ethernet in the Age of AI, Adapting to New Networking Challenges, presented by the SNIA Data Networking and Storage Forum. My name is Eric Smith, and I'll be your host and moderator for today's webinar. And I'm pleased to introduce you to our expert speaker Raghuraman Sundaram, a software architect at Celestica. Before we get started, a little bit about SNIA. SNIA is an industry organization that develops global standards and delivers education on all technologies related to data. SNIA is comprised of 200 industry-leading organizations, 2,000 active contributing members, and 50,000 participating IT end users and technologists worldwide. The SNIA Data Networking and Storage Forum, or DNSF, is an active group within SNIA that provides vendor-neutral education and insights that are intended to drive the awareness and adoption of a broad set of technologies, including storage protocols, AI, and implementations. We do this by providing expert webinars, white papers, blogs, and presentations at various industry events. So some logistics for today. You are welcome to ask questions during the presentation by selecting the Ask a Question option and entering your question. We will either answer that question verbally during the presentation or afterward in a Q&A blog post. If you are looking for the slides, they can be found via the Attachment tab at the bottom of your BrightTalk console. Before we get started, let's take a quick look at the SNIA legal notice. This provides SNIA's copyright notice regarding the use of material. SNIA is not providing any legal advice, and there are no warranties expressed or implied. So if you want to reference this material, please do so at your own risk. And with that, I'll turn it over to Raghu to walk us through the agenda for today's session.
Thank you, Eric. Thanks, everyone, for joining the webinar. So I'll go over the agenda quickly. As you see in the slide here, in today's session, I will talk about a little history of the data center networks and its evolution. We'll also talk about the need for AI fabric and what is it actually. We'll touch upon the traffic and the congestion management requirements for the AI fabric and the UEC's role in addressing these requirements. So let's get started. So regarding the history of the data center networks, this is one of the networks which is used in the data center sometime back. This is a 3-layer topology. The topology itself is called access, aggregation, and core topology. The typical use case for this topology is for a client-server architecture where the traffic is north-south. If you look at the figure, anything below the aggregation layer is a single L2 domain, and the spanning tree protocol is used to avoid loops in the L2 domain. Some of the shortcomings of this topology are poor link utilization. STP cuts the loop, and some of the links in the loop are underutilized or not utilized at all. So there is a poor link utilization there. Second one is when you lose the aggregation or access switch, you lose almost half the bandwidth. The third one would be being a single L2 domain below the aggregation layer, the VLANs cannot stack, meaning any two servers cannot use the same VLAN without colliding with each other. So as the cloud native applications and VMs grew in the data center, so does the east-west traffic within the data center, the traffic between server to server within the data center. The previous topology is not good in handling the east-west traffic. So came the leaf-spine architecture, where the server connects to the leaf switches, and the leaf-spine switches forms an all-to-all, what we call it as a cross connectivity. Some of the advantages of this topology are high available bandwidth, as ECMP is used in the links between leaves and spine instead of any loop prevention. Because the leaf, anything above the leaf is in the L3 layer, and the L3 is naturally good at doing multipath. So ECMP is one of the option, and it gives a highly available bandwidth all the time. The second one would be the VXLAN, which basically enabled multi-tenancy, where the VLANs at the server layer can be reused across the L2 domains. For example, a server connected to Leaf1 can use the same VLAN as the server connected to Leaf3, and both of them can be in two independent domains, so multi-tenancy. The next network itself, the topology itself is highly reliable. For example, if I lose a spine switch, it impacts only that segment of the connectivity. There are other spine switches are available to reroute the traffic. At the leaf level, multi-chassis lag is preferred for the failover conditions. As you see, the leaf, I just indicated leaf and leaf 2 are connected in a multi-chassis lag kind of a network. This networks are easily scalable. If I have to just scale this network, I add more leaves and spines, without touching the existing connections. So you can scale the number of servers connected to this topology easily. So this network is the one that gives connectivity between the servers and storage in the data center. Given that today there is a lot of talk about GPU fabric for AI and HPC workloads, let us talk about one of the heaviest AI workload, which is training. Let us take a step back and look at the LLMs and how it is impacting GPU scale in the network. LLMs are large language models which are trained on, again, large data sets using deep learning algorithms to produce human-like output. The data set itself has large number of words. These words or characters are converted into sequence of integers, which are called tokens. A typical data set contains hundreds of billions to trillions of tokens. LLMs themselves has parameters or weights, which are learned variables to dictate how the model predicts and generate outputs. So during the training, the weights are adjusted such a way that we end up having predictable output all the time. Given the terminology of tokens and parameters, etc., let us look at some math. The top picture is a representation of how the data set with numerous words are converted into tokens. As you come clockwise, we have a table which have listed a couple of popular models, GPT-3 and Llama, in terms of what is the token and the parameter scale, etc. As we move further clockwise to the bottom box, for example, let us take GPT-3, for example, a model with 175 billion parameters. It would take almost close to 1 TB of memory to store those parameters. During the training, the state of the training is constantly checkpointed to storage. Each of these checkpoints would require 4 TB of memory. A typical high-end GPU today would have somewhere around 80 GB of memory. So it is evident that no one GPU can fit this kind of scale. If I go again clockwise, there is a simple math in the left box. For GPT-3, which has 175 billion parameters and 300 billion tokens, with a typical 6 floating point operations per token per parameter to train the model, one would end up with 3.15 into 10 power 23 flops. A GPU with 67 teraflops per second would require somewhere around 4.7 into 10 power 9 seconds to train the model. If one would have to train the model, let's say in 1 month, it would require somewhere around 1800 GPUs. This is given that the GPUs work almost like 24/7 without any ideal time. When we consider the time taken to load the data set or a model or checkpoint the training state to the storage, this number of GPUs required would be much more than the 1800 shown. So in the previous slide, we talked about the size of training workload and how it influences the number of GPUs to perform the same. As indicated in that slide, no single GPU can hold the entire dataset or the model. In the next couple of slides, we'll talk about the parallelism types through which a GPU cluster can be used synchronously for the training. So the first kind of parallelism we are going to talk about, data parallelism. As the name indicates, the data set is split into multiple mini batches, and each GPU will train the model and make predictions through the forward pass. And the gradients are collected via the backward pass. This one forward pass and a backward pass combination of the entire data set is called a echo. At the end of one iteration, the gradients are aggregated and averaged, and the result is passed to all the GPUs in the group. So this process of forward pass, backward pass, and aggregation happens multiple times over and over again for the model to converge. So the second type of parallelism is a model parallelism. So this is something opposite to the data parallelism. Instead of splitting the data, in this case, the model is split into several partitions, and each GPU gets one partition of the model. During the forward pass, each GPU computes the output and pass it on to the next GPU in the line. During the backward pass, the gradients are passed on to the previous GPUs till the first GPU. The model parallelism has a sequential dependency because it goes from one GPU to the other. So third one is pipeline parallelism, which is a combination of both model and data parallelism. Because the model parallelism, the ideal time of the GPU is much more. So in the pipeline parallelism, the model parallelism, the first GPU has to wait till the entire forward pass and the backward pass cycle till it receives the gradient. So in the pipeline parallelism, to reduce the ideal time of the GPU, the mini batch of the data set we talked about in the data parallelism is split into micro batches, and any GPU would work on a micro batch and the model partition. Once it is done passing the output to the next GPU, instead of waiting for the backward pass, it will start work on the next micro batch. This parallelism increases the inter-GPU traffic. You can see the figure of the pipeline parallelism on the left side bottom. You can see the bottom row indicates the first GPU. After crossing the first micro batch, it gives to the next GPU in the line, which is the row above it, and picks up the next micro batch at the same time for the first. This brings down the ideal time of the GPU, but increases the inter-GPU traffic. The next parallelism we are going to talk about is the tensor parallelism. It is again more like breaking down the pipeline parallelism into smaller pieces. It distributes the compute intensive parts of the pipeline or a model parallelism across multiple GPUs. It brings down the per GPU computation and the memory requirements. Tensor parallelism actively scatter and gather information from other GPUs, thus increases the inter-GPU traffic significantly compared to the other parallelism techniques. For instance, a matrix multiplication split by row would require all reduce in the forward pass. What is the conclusion? As you may understand from the above parallelism techniques, there is a significant inter-GPU traffic regardless of whichever parallelism being used. Any drop or congestion during the training will significantly impact the performance. Of course, latency and link utilization plays a significant role in improving the performance. So we talked about parallelism. We are talking about inter-GPU traffic, uh, moving the output from one GPU to another. How that happens? How the GPU communicate with each other. We talked about passing predictions during forward pass and aggregation of results in the backward pass. These happen via something called collectives. There are a list of collectives I have listed down here. I'm not going to go through all of them. Most of you would have already read or heard about these collectives in one way or the other. Something like all reduce, right? There's aggregating data from all member GPUs and send the result to all member. Reduce and scatter, right? Aggregate the data from all member and scatter the results to all other members, all the members. Broadcast, name itself suggests sending the data to all the members in the group. So these are the collectives via which the GPU communicate and generate inter-GPU traffic. So in the past few slides, we talked about the scale of the GPUs required to train the model. And not only that, but how these GPUs has to operate synchronously via inter-GPU communication to work efficiently. With that in mind, let us move to the GPU cluster or AI fabric topology and see how it is going to look. As you see in the figure, there are three networks in play here. The first one is the front-end network, as we call it, which is nothing but the same class topology we saw a few slides back, which you use to connect server and storage network in the data center. There is no change here as it still uses ECMPs and VSLANs, etc. So what you see in the bottom is called the backend network, so which is connecting the GPUs across server and across racks. There are two types of backend network. First one is a scale-up network, which interconnects the GPUs within a given server. This uses interconnects such as, for example, NVLink or Infinity Fabric and forms and high bandwidth mesh. Currently, we are getting models in the market which can scale up to 64 to 72 GPUs in a rack in the scale-up domain. Still, this is no way close to the GPU scale we talked about to train LLM. To achieve that kind of a scale comes the other type of the backend network, which is called scale-out. In this network, each GPU via a NIC connects to a cluster of GPUs in other racks or servers. These interconnects are achieved via networking switches. One of the most important difference between a scale-up and scale-out network is in scale-up, the typical memory access is mostly direct, and in scale-out, it is mostly through RDMA. With the networking switches in play, in the scale-out network, Ethernet becomes one of the primary choice for such deployment. Why Ethernet? Because it is simple, scalable, modular, just cost-effective, and most importantly, it fits very well into the already existing data center ecosystem. Given that there are some challenges with Ethernet for the scale-out networks, because by nature, Ethernet is lossy, and AI workloads do not respond very well to the packet loss. So this figure shows a more clear view of scale-up and scale-out network. As you can see, the GPUs in a given server is connected to connected via high-speed inter-GPU links in the scale-up domain. Inside the gray boxes, you can see a blue box with a NVLink interconnects. So what I'm referring to. and the same GPUs are connected via NIC to a leaf switch in the scale-out domain. And the leaf spine topology is now very similar to the class network we have seen in some of the previous slides. The network in this figure, if you look at, gives a all-to-all connectivity between the GPUs. For example, you can, from one GPU, you can reach to any other GPU in the network via this leaf and spine topology. This is one of the standard ways to provision the network. Typically, in case when I am an infra provider for LLM training, where multiple different type of models can be trained on that network. This is one of the catch-all network which will cater to any kind of traffic patterns. So this is an all-to-all class fabric with a factory topology. As you go from leaf to spine, the bandwidth increases. There is one more division to this scale-out network, which is what we call as a rail optimized topology. This is a slight deviation from all-to-all connected topology in the previous diagram. There is an interesting paper on this topology, which I have given in the reference section. That paper talks about two domains in this topology. One is a high bandwidth domain and a NIC domain. Right? High bandwidth domain is internal to a server, and the data transfer is much faster. And the NIC domain is something connected over the NIC. So you can compare these two domains as to scale up and scale out. In this topology, if you look at the GPUs with the same rail or RAN, connect to the switch called a rail switch. As you follow the red line here, the GPU1s of different servers connected to the same rail switch. The motivation for this topology is based on the collectives, which are used in different types of parallelism. For example, the tensor parallelism does a lot of scatter and gather approach, which are very bandwidth intensive. So the GPUs participating in a tensor group are typically kept within the server in the high bandwidth domain. Right. So, for example, a pipeline parallelism uses a lot of point-to-point traffic as the information flows from one stage of the pipeline to another. In this case, one can use a particular rank of GPU or a GPU rail to pass on the traffic from one stage to another so that it stays within the rail. So otherwise, in the previous topology we talked about in the class, from GPU to GPU, I will always go from GPU to leaf to spine to another leaf. So instead of 3 hubs, this cuts the usage into 1 hub. So most of the parallelism and the collectives operations can be either kept within the high bandwidth domain, or in some cases, if it goes over the NIC domain, most of the cases it can be kept within a rail rather than reaching the spine switch. So there is one more variation to this, which is called a rail-only topology. For example, in this case, a traffic from GPU1 of server 1 to reach GPU2 of server 2 in a rail optimized topology, it would go from GPU1 to rail 1 to the spine, one of the spines to the rail 2, then to the GPU2 on the server 2. So instead, it can take a path in the high bandwidth domain from, instead of going over the rail, it can take a path from GPU1 to GPU2 in the high bandwidth domain, and it can use the rail 2 to reach the destination. With this kind of traffic forwarding in play, typically you end up not requiring the spine layer at all. So that's why it's called rail-only topology. So one of the advantages keeping in the rail-only level is like I get more ports to connect to the GPUs in the rail switches. So till now we talked about AI workload scale and how it influenced the backend networks. We talked about some of the backend topologies in play. These are at the physical or a forwarding level. But what about the traffic requirements? A few slides back, I mentioned Ethernet being a lossy technology. It still has some shortcomings to cater to the AI fabric. What are the characteristics of AI fabric traffic, especially the scale-out fabric? It requires high throughput, something around 100 Gbps. It is of a short length with a typical round trip time of 10 microseconds. So what are the requirements would be for a scale-out fabric? It has to utilize all the bandwidth available so that the traffic is fairly distributed. Because the GPU traffic is largely fat flows, unlike server to server front-end traffic. To do that, it should use the load balancing more effectively, like more path aware or adaptive. It should have a quicker loss retransmission scheme to avoid high latency. It should have a good congestion control algorithm for AI fabric specific. So Ultra Ethernet Consortium is working on some of the, all of these requirements. I should not say some of these requirements. A brief introduction of Ultra Ethernet Consortium is like there are several. It is working on several layers, not only in traffic engineering or congestion control layer. It is working on several layers, starting from the lib fabric API to the transport layer to the link layer. Right. So what we are going to talk about comes under Ultra Ethernet transport layer, and even more specific to the Ultra Ethernet transport layer, there is a packet delivery sublayer. This is where all these methods and optimizations are coming into pictures. So given that, right, let me quickly take you over to the current congestion scheme, congestion avoidance scheme available in the data center network, which is typically for the RDMA traffic. RDMA is, as everyone knows, Rocky's RDMA over converged Ethernet, which uses a DC QCN for congestion handling. It has two pieces to it. One is ECN, explicit congestion notification, which takes the congestion signal to the receiver. If there is a congestion happening in the network, the ECN is marked in the packet and the receiver receives it. And from the receiver, it triggers a CNP congestion notification packet to the sender, which makes the sender to slow down. And secondly, priority flow control to ensure lossless traffic. How it operates is, the ECN hits first, makes the traffic to slow down when there is congestion in the network, and PFC priority flow control takes care of not dropping any packet on the flight. Right? So how it works is whenever there is because of congestion, any switch queue builds up. The switch sends a pass frame to the previous switch to stop transmitting traffic. So the previous switch stops the traffic. the same path frame goes all along till the sender, so that you don't end up losing packets on the flip. There's some of the issues with the DC QCM schemes are PFC is priority based, per port per priority based. It is not flow based, and there can be a PFC storm when there is a heavy congestion resulting in deadlock. It increases the tail latency significantly because of its stop and start nature of congestion control. Again, ECN is also not flow based. It is sender and receiver based. So when the ECN is generated, it might affect other flows going from between the same sender and receiver. And configuring PFC and tuning buffers is cumbersome. So given the characteristics of Rocky V2, it will not satisfy the requirements for traffic in the GPU fabric. So what are the improvements proposed? The first one is for better link utilization, packet spraying. The TCP or RDMA implementations are expected to receive the packets in order. So any out of order or a hole in the packet sequence is considered as drop and trigger congestion control or loss retransmission. ECNP, as discussed earlier, ensure in-order delivery of a flow between a sender and a receiver. So the path is chosen based on the hash value calculated using the packet fields, and the UDP source port in the packet field acts as an entropy to choose different paths. ECMP is not an ideal load balancing technique because elephant flow on a given path can affect other flows. For example, right, if you load a 800 Gbps link with 8 streams of 80 gig traffic across 32 servers, the worst link is oversubscribed by 1.4 times. As you are aware, the parallelism techniques are dependent on inter-GPU low latency traffic, and the performance is as good as the slowest link. So if one link is oversubscribed, it is going to affect the entire training process. So packet spraying solves this problem by spraying the packets of a given flow into all the available paths to the destination. The effect of this is the receiver would receive out of order packets. So the receiver should have a sophisticated hardware to reassemble them. In the packet spraying, even though it utilizes the link optimally, there is a challenge to identify congestion when it happens. So when there is a congestion, it cannot understand whether it happened in an intermediate switch or the last link between the switch and GPU, which is called in-cache congestion. So since out of delivery is a norm in the packet spraying method, how would a receiver would know whether the given packet is dropped or just delayed because of the out of order? So waiting too long for a packet to arrive on the receiver side would increase latency. So there's another scheme where the sender has real-time information about the congestion state of all the available paths. So as you see in the diagram, the sender periodically by a mechanism, pole or a telemetry mechanism, the sender will know what are the paths available to a given destination and its congestion status. So in the flow-based load balance scheme, so when a flow hits a switch, it's the switch typically picks the egress link based on the load on that particular port. So, for example, I have three different links from a switch to the destination. I pick a least loaded link at the switch level, but I am not sure uh, in the downstream. I don't know what is the congestion status. So this technique basically, instead of looking at the node level, this scheme will improve the performance by choosing the least loaded path from entire source to destination. It might be even possible to switch any given flow from one path to another, even during a transient congestion. In that case, a careful tuning is required to get so that no, you don't end up with the out of order packet. Or even in case of out of order delivery, there should be a receiver should be able to handle that. So again, to implement the scheme, there should be something running in the background, periodically to give a accurate and real-time information of all the congestion status of all the available paths. That's one of the overhead. So how do you collect the path congestion status? So we have congestion signaling, which is called CSIG, or in-band telemetry. It's a method in which each node in the data path adds metadata information in the packet itself about the congestion levels. For example, you see the diagram, the packet from sender goes over 3 switches, and each switch add some data to the packet itself. This data would typically will have a queue depth, buffer levels, and link utilization, etc. So there are 2 ways to do this. So one is, we can do it on the actual data packet or via some periodic probe mechanism. Once the receiver receives this packet and sees this metadata, it can reflect the data back to the sender. So the sender is aware of the congestion levels in various paths in the network. So based on the feedback from the receiver, sender can actually implement a specific algorithm to handle different congestion scenario. As shown in the diagram, the 3 switches are in various congestion levels, the red being the highest. When this information is available to the sender, it can avoid congestion by adjusting the transmission rate such a way that link between the congested switch and the receiver is fairly used among all the senders. If I don't have this, one would end up in a congested scenario like start-stop traffic, which increases the latency or a lost packet and retransmission, etc. The cost to implement this would be some specialized hardware which can basically insert metadata at each hop at a fairly high rate. So HPCC, high precision congestion control. AI fabric is in a high bandwidth and a short RTT environment. The congestion control protocol has to determine how fast the traffic to be sent at any given point of time and ramp up to the wire speed very quickly. For example, the AI and HPC applications send a lot of data, and sometimes it can send, let's say, 1 MB or 8 MB of data. In a typical case shown in the slide, 1 MB of data over 800 Gbps link take 10 microseconds, which is typically 1 RTT. In this case, it would take to transfer 8 MB of data, it would take 8 RTT to move the data to the destination. TCP, if you use the TCP slow ramp, TCP itself would use several RTT to ramp up to the full speed. We cannot afford the TCP kind of slow ramp up, which can put load on the network. At the same time, when there is a congestion, we need to back up really quickly, as the traditional congestion control like ECN, etc., would be too slow to react. Shown in the other figure, HPC has two flavors of congestion control. First one is sender-based, more like how TCP works, where the senders, multiple senders, works on their own algorithm in a distributed manner to figure out the loss and congestion in the network. When there is a congestion, they utilize their share of bandwidth or 1/n of the bandwidth, not overloading the network. Senders use delay, mark, and trim as indicators for congestion. Typically, again, as I already told, it's inspired by TCP, but tailored to high bandwidth short RTT requirements. The second one is the receiver-based algorithm, where the receiver allocate credits to the incoming senders and control the rate at which the sender can send traffic. It's a great algorithm to manage in-cast congestion. For example, when there are multiple senders, the receiver decides the rate at which the sender can send, so that the last link is not overloaded or under-replaced. So these are the congestion control techniques UEC is currently working on. So going ahead, so we talked about how to avoid congestion in the previous slides, but losses are inevitable. This retransmission happens before the TCP kicks in and adjusts the window size based on the loss. The selective acknowledgements, unlike go back n frames mechanism, where the packets are resent from the point of loss, the selective acknowledgements indicate the sender to retransmit only the lost packet. This targeted approach optimizes bandwidth and reduces latency. But to achieve the fast retransmission, the receiver has to know in the first place that the packet is lost. It becomes tougher when the technique like packet spray are in play, because packet spray is going to have a out of order delivery, and the receiver would not be able to know that based on the sequence of number that the packet is lost. How would the receiver know that packet is lost in a quick time? Packet trimming comes into play. The packet trimming kicks in when a packet is lost, is about to get dropped because of congestion in the network. Instead of dropping the packet entirely, the switch trims the packet to 64 bytes with relevant information and sends it over a high priority to the receiver. So the moment receiver receives a trimmed packet, by looking at the packet, it knows this packet is dropped and whom I need to contact for a retransmission. So by looking at the trimmed packet, the receiver would trigger a selective act to retransmit the packet to the sender. Sender can use the selective as an indicator of the congestion. Not only retransmit the packet, but getting a selective act for a particular packet indicates a congestion on the path. Sender can take multiple steps, like moving the flow to a different point to avoid further congestion. So we talked about congestion avoidance, congestion control. We talked about in case of loss, how to retransmit, how to identify loss, etc., etc. This is one of the severe form of congestion in a network is between the last switching node and the GPU or a NIC connected to it, which is typically called in-cast congestion, when there are no alternate paths can be taken. The only way for the sender is to reduce traffic and use that link fairly. Again, because of that, the latency will increase. For example, as shown in the figure, right? In case of all reduced collective, which is a collective. It's going to aggregate the gradients from all the available GPUs in the group, and again send the results back to all the GPUs. A single GPU aggregates the information from all other GPUs, right? This is going to create a lot of traffic from multiple GPUs to one particular GPU. As you follow the black arrows on the left side of the picture, both the pictures, you can see the last link has multiple black arrows towards it and in the opposite direction. So all reduced kind of a scheme now increases a lot of congestion in the last link, which is in cast. So in network collectives, what is it? In network collectives is a method where some of the collective operations are offloaded to the switches from the GPU. So as you see in the bottom diagram, it is implemented in form of an aggregate tree, as shown in the figure, where each node aggregates the downstream flows and forward them to the upstream node. So you can imagine a rail switch in the rail optimist topology doing in network collectives, right? To aggregate a pipeline parallelism or a DP parallelism traffic. Instead of sending it to a GPU, the rail switch can aggregate the traffic and reduce the traffic between the rail switch and to the GPU. This reduces a lot of stress from the network. One of the thing with in-network collective system, it should be a little bit careful in implementing in-network collectives and packet spraying together, because in-network collectives expect the traffic to follow a particular path. It's the same switch. So with that, we are almost at the end of our session. This is the table talks about what are the requirements of AI and HPC networks. What is UEC transport is providing against the legacy RDMA, and what are the advantages? I think most of them we talked about. We didn't talk about the security. UEC transport comes with the inbuilt security. That's for another session. But other than that, we talked about all the above points. So to summarize this session, we talked about the LLM scale, why we need large number of GPUs to basically do a training kind of a job, and what is fabric, GPU fabric. We know what are the types of GPU fabrics and how they are connected, the scale up and scale out fabrics, and why Ethernet is being one of the primary option. And we talked about class scale out and a rail optimized scale out topology. We talked about traffic requirements in a AI cluster and how UEC is working in addressing these new requirements for AI workload. These are some reference links I have referred to basically come up with this slides. This is for further reading. With that, I will complete my session, and thank you for it.
Thanks, Raghu. That was great. We do have a few comments, questions right now. Somebody was asking if we were going to review rail-based fabric topologies, and you did that. There's certainly a lot to say about rail and how you would scale rail-based topologies. So I think that's probably a little bit, that could be another session on top of this.
Yeah.
The comment about NVLink being a standard, it's used extensively by NVIDIA, but it's not an industry standard. It's proprietary. And I think there's definitely work going on.
UEC is working on a UA-Link, UA-Link standard, a specification to interconnect GPUs.
That's exactly where I was going. So
Yeah.
thank you for that. And then another person pointed out that there are multiple ways to do class L3 networks. You know, there's one way to do it where there's L3 aware multi-homed hosts that can also be integrated into the topology without using L2 overlay technologies, which becomes complex and error prone the larger and diverse the network becomes. And so it's a fair point. There are definitely multiple ways to address that. The need to have to provide routing between geographically dispersed GPUs in different subnets. So, are there any other questions? You can feel free to go ahead and jump them into the Q&A tab. We'll give people a couple seconds to do that. And then while we're waiting for that to happen, if we don't see anything, just before you leave, please rate the webinar and provide us with your feedback. We definitely use it. This webinar and a copy of the slides again are available at the SNIA Educational Library. And we will be working on a Q&A. So for those of you that didn't have a chance to get a question in now, or would like to, I think we just had one come in. Including answers to the questions we couldn't get to today will be posted to a blog. And so we'll post it there at that URL. And then always follow us on social media. We're at SNIA and we're also on LinkedIn. Okay. So I'm not sure. Do you want to try and do you see that question, Raghu?
I'm just going. Okay, the new question which came in, what is the support library tool or kernel module for enabling Node 1 GPU 1 to Node 2 GPU 2? It seems some post-level knowledge, not at all. Yes, you're right. I'm not a post person. I work on a networking switches layer. I'm not aware of what is the support available to do that kind of a forwarding. I can do some research and get back.
Right. I mean, if the question was, how are you routing between GPUs in the same? I mean, well, there are communication libraries that are used for this, and with NVIDIA, it's going to be Nickel.
Yes.
And so but the question is specifically going node to node. And I think we should probably do a little bit of research on that and get back to you with a solid answer.
So another question, what is the difference between collection and multicast? Okay, how to put it, they are in two different domains, right?
Yep.
Yeah, if you see some of the collectives which use traditional, the way multicast works, but typically it is all driven from the GPU. The network doesn't decide, where to replicate the packet. It's actually the GPU which generates the collective traffic, decide, who are all the receivers. So the data is sent to all the receivers as individual copies, whereas in a multicast, if you look at in the switching terms, the traffic comes from the sender and it diverges when there is a different paths, right? When the receivers are in different paths. So the copy happens in the network. Here it is not like that. So to be, very,
yeah,
on a way it behaves. But actually the multicast and collectives are two different things altogether.
I guess a little bit of confusion is it, are you talking about the in-network collection, the collectives, or the collective operations? Because we discussed both. And if you're talking about the in-network collectives, that's where you have a
yeah, there are some relevance there. Yes, Eric.
Yeah, but I mean, it's almost like the reverse. I mean, the point
yes.
of doing in-network collectives is to reduce the amount of traffic, whereas In multicast, it's like it's almost multiplying it to go out to multiple destinations. So that's another difference. But again, we could take another look at that and get back to you guys. So, all right. So I don't see any other questions. So we'll go ahead and wrap the session up. And thank you all for your time. And again, please do rate the webinar and provide us with your feedback. And we'll talk to you all next time. Thank you.
Thank you. Thank you.